Hello everyone, my name is Brandon Sieu, and I will be the co-presenter for today along with Hossain Bari to present our work on AestheticNet, a deep convolutional neural network for person identification from visual aesthetic. This project was supervised by Dr. Marina Gavrilova from the Biometric Technologies Laboratory in the University of Calgary. All the portraits and contacts for the authors are available on this slide. The following is a small overview of the presentation. First will be a broad introduction to biometrics and person identification from visual aesthetic preference. Then we will describe the motivation of such a project in the context of computer graphics and human-computer interactions. Afterwards, the primary research questions and contributions will be stated, along with the related works in the domain. The methodology of our novel deep learning approach, along with the experimental results and comparison with previous methods, will follow. Lastly, we will conclude the presentation with the possible future directions extending from the work. First of all, it would be useful to define what is exactly meant by visual aesthetics. Visual aesthetics can be described as a person's taste or judgment of visual content. This can be something as simple as liking a picture of a cat or a dog. In the modern world, online platforms make this information widely available through liking or subscribing systems or friends networks. The usage of this information for the purpose of identification is an emerging area of research in socio-behavioral biometrics, which uses a person's social behavior and interactions for analysis. Below are some examples of categories in biometrics. Physical biometrics includes aspects of a person's body, such as fingerprint analysis, and behavioral biometrics includes the behavior of a person's body, such as gait analysis. Socio-behavioral biometrics include social interactions that are present, for example, in a social network. Under this premise, a question can be asked. What is the advantage and value of using this information, and how does this factor into computer graphics and human-computer interactions? Visual aesthetics is a non-physical trait. This allows systems to use the information quickly and remotely. A person's aesthetic preference can also be observed covertly without the need for direct user interaction. Next, specialized equipment is not required to measure this biometric. All these points make aesthetic preference accessible, universally available, and convenient. Knowledge of a person's aesthetic preference can be used for generating catered content. For example, personalized generative art will be able to generate more accurately with its preference information, and user-adapted content can be created that suits individual tastes. The following is an example of a conceptual service robot system using aesthetic analysis. When provided with a user's aesthetic preferences for the first time, a service robot would be able to learn this connection between the aesthetic and the user. These aesthetic features are extracted, processed, and stored in a database for later use. This can be useful once the service agent encounters a similar visual stimulus again, where a semantic link can be formed back to the particular user from the aesthetic database to produce an adapted response. This can allow for the robot to recognize and change its response depending on the desires of the user. Person identification from visual aesthetic is a relatively new domain. The first proof of concept work was published by Lovato and others in 2012. Lasso regression and 62 image features were used. Although the accuracy was low, the work served to verify that a person's aesthetic preference was indeed discriminatory and published the benchmark dataset for all of the subsequent works. Seglin, Marina, and Cristani followed in 2014 by using counting grids to train multiple SVM classifiers. 111 image features were used, with more perceptual and content-based features added. In 2017, Azam and Gavrilova introduced 861 image features, split into perceptual, content, and HOG-based features. PCA was used to reduce this to 700 principal components. Lastly, the most recent work by Sieu and Gavrilova utilized gene expression programming to construct 150 composite features from 924 original features by leveraging genetic evolution for optimization. In summary, machine learning approaches and feature engineering are clear factors for high accuracy in this problem. A trend in increased feature size and feature dimensionality reduction can be seen to increase performance of the classification systems. However, the previous works rely heavily on handcrafted features that require domain-specific knowledge and manual feature discovery, which can pose issues with scalability. In addition, mostly traditional classification techniques such as SVM and lasso regression are used. The reliance on handcrafted features and the need for sophisticated methods in machine learning have led our investigation into deep learning approaches. In response to the specialized problem of person identification from visual aesthetic, we ask the following primary research questions. First, can a deep learning method based on a convolutional neural network achieve similar or higher recognition performance over the current state-of-the-art methods for person identification from visual aesthetics? Second, can the convolutional neural network, where the input is not a single image but a set of preferred images mapped to an individual, be trained? And third, do the high-level features extracted from a CNN have more discriminatory ability than handcrafted features? To address these research questions, the paper has made the following contributions. First, a pre-trained model of VGG16 architecture is utilized for feature extraction, followed by PCA on the high-level features. This allows a representation of each image to be reduced to a low-dimensional vector of principal components with high variance. Following this, to allow the CNN to accept the set of users' preferred images, a one-dimensional vector of each user-chosen image is concatenated to transform the user's preferred image set into a unique two-dimensional matrix representation. Then, a novel residual learning-based convolutional neural network architecture is designed. The CNN architecture is trained on the 2D matrix representation of each user image set and performs identification. Finally, experiments are conducted on the benchmark dataset published by Lovato and others. These experiments show that the system is more accurate, more robust, and requires less running time when compared to the state-of-the-art methods for person identification using visual aesthetics. The following figure shows the proposed three-stage framework of AestheticNet. The process begins with a feature extraction of the images through a pre-trained modified VGG16 network. This results in a 7x7x512 matrix containing high-level features. Then, dimensionality reduction is applied to the resulting high-level image representation, utilizing PCA. The resulting matrices are flattened and concatenated together to a complete image set matrix. This matrix is used as input to the identification system, consisting of a novel residual learning-based CNN that is trained and tested on the concatenated image set representation. In the next slides, we will elaborate on these processes. In the feature extraction step, the image must be pre-processed to a standard representation. Each color image is resized to a fixed size of 224 by 224 by 3. Each image is first normalized with zero mean and unit variance. Doing so reduces the impact of outliers and the variances in image illumination. A modified VGG16 model receives these standardized images as input and extracts the high-level features. The last layer of the network outputs a matrix dimension of 7x7x512, which equals 25,088 pixels. This number of pixels is significantly lower than the original image of 150,528 pixels by 6 times, condensing the feature representation greatly. Now, I will pass the explanation on to the other co-presenter, Hossain Bari, to elaborate.
Hello, I am Hossain Bari. I will present the rest of the presentation of our paper. We propose to use the weights of the pre-trained VGG16 model to extract the high-level features from every color image. Since individual chooses images from different categories, it is hypothesized that the sample distribution of the dataset of the person identification would be similar to the ImageNet dataset. Thus, it qualifies the use of pre-trained VGG16 architecture in our study. However, the original VGG16 architecture is modified by removing the decision layer, fully connected layer, and the flattened layer from the back of the original network. Therefore, the max pooling layer becomes the final layer of the VGG16 model. The output of the deepest max pooling layer is the high-level features extracted from the color image. The high-level feature extraction module extracts 7x7x512 dimensional feature map. In our study, n images from the chosen image set of an individual are used for person identification, where n is equal to 100. Therefore, 100 by 7 by 7 by 512 is still in high dimension. This is the motivation for further reduction of the high-level feature map. To reduce the feature map, at first, high-level feature map is reshaped to p by q dimension, where p is much less than q. Then, principal component analysis is conducted to extract p by p feature map. In our study, P is set to 16. So after the PCA, the dimension of the feature map becomes 100 by 256. This is a significant reduction of the high-level feature map. The reduced feature map of 100 times 256 dimension is used to train the designed residual learning-based CNN model. The random shuffling of n images is performed to train the CNN model without learning the sequence of n images. This is the architecture of the proposed CNN model for the person identification. At the first layer, convolution layer extracts the low-level features, and the low-level features are filtered using max pooling layer. Then 4 residual learning blocks are cascaded with the filters of 64, 128, 256 and 512. Feature map is drastically reduced using the global average pooling layer. Residual learning block with skip connection is used in this architecture to avoid the degradation problem. At the decision layer, softmax activation function is used. Each of the residual learning blocks consists of identity and shortcut blocks. A common module named conv2d bnrl is being used in both identity and shortcut blocks. This common module takes a tensor, the number of filters, and the stride size as arguments and performs a convolutional, batch normalization, and radio activation. This is the diagram of the identity block, and this one is for the shortcut block. The identity and shortcut blocks are similar except for one key difference. However, there is no skip connection from the input tensor in the shortcut block. In the shortcut block, the result of 1 by 1 convolution and batch normalization operations are added as a skip connection. To validate the proposed method, the publicly available 40,000 Flickr image dataset collected by Lovato et al. Is used in our study. This benchmark dataset is consisted of 200 favorite images per user for 200 random users. The images are not restrained or balanced in any category. And between users there is a 0.05% rate of repeated images. Example images of user 15 and user 19 are shown in this figure. The performance of the designed CNN architecture is evaluated on a dataset using a 5-fold cross-validation approach. The average recognition performance is reported to evaluate the performance of the proposed method. The proposed method achieves recognition accuracy of 97.73%. To demonstrate the experimental result, first we show the learning curve. The learning curve is demonstrated to show the minimization of the categorical cross-entropy objective function over each of the epochs at the training and validation phases. The difference between training and validation loss is very low. On the other hand, the impact of loss minimization over the accuracy improvement is shown in this picture. Though the training accuracy reaches to 100%, the highest validation accuracy is 97.73%. From these two figures, it is evident that there is no overfitting problem in this proposed method. Rank 1 and rank 5 recognition accuracies are computed for AestheticNet on the benchmark dataset. Furthermore, the performance is compared with 4 state-of-art methods. Lovato et al. Achieves 14% rank 1 recognition accuracy and just above 50% rank 5 recognition accuracy. Segalin et al. Achieves 59% and 41% higher rank 1 and rank 5 recognition accuracies than Lovato et al. On the other hand, Sieu and Gavrilova achieves just above 80% rank 1 accuracy, and Sieu and Gavrilova further improves that rank 1 and rank 5 recognition accuracies. However, it can be seen from this table that the AestheticNet secures the highest rank 1 and rank 5 recognition accuracies of 97.73% and 99.85% respectively. The recognition performance of the proposed AestheticNet is also compared in terms of CMC score with the most recent method Hossain and Gavrilova and Sieu and Gavrilova. The CMC score from rank 1 to rank 10 of the proposed method is shown in the blue color. This one is the CMC score of the Sieu and Gavrilova, and the lower part one is the CMC score of the Hossain and Gavrilova. From this figure, it can be seen that the proposed method is superior to the state-of-art method at each rank. This is the indication of the better recognition system comprised of high-level feature extraction module, representation of high-level feature map in low dimension, and designed residual learning-based convolutional neural network. In our study, the inference time is calculated using the system configuration of Intel Core i7 3.2 GHz CPU with 16 GB of RAM and NVIDIA GTX 1080 GPU. The inference time of the identification of an individual from a set of 100 images is the summation of the running times of high-level feature extraction, dimensionality reduction, and the identification system. The total inference time is 1.22 seconds. The inference time is now compared against recent works, which is shown in this table. The inference time of the method Hossain and Gavrilova is greater than 25.75 seconds, whereas Sieu and Gavrilova's running time is greater than 29.12 seconds. However, the inference time of the proposed method is 1.22 seconds. Therefore, our proposed method is at least 21 times faster than Hossain and Gavrilova and 23.85 times faster than Sieu and Gavrilova. Since the handcrafted features generation is avoided in the proposed method, the inference time of the proposed method is significantly lower than the recent state-of-art method. In this study, a unique three-stage framework called AestheticNet for person identification using visual preference is proposed. A set of preferred images of an individual is trained using the proposed method. Design novel CNN architecture achieves the average rank 1 recognition accuracy of 97.73% on the publicly available benchmark dataset. The achieved recognition performance is the highest among all the state-of-art methods. The effectiveness of the proposed method is further demonstrated using the CMC score from rank 1 to rank 5. Based on the experimental result, it is evident that the proposed framework is able to extract more discriminating features from a set of aesthetic images. Now about the future work, the improvement of the high-level feature extraction module will be investigated. Additionally, it can be analyzed whether similar recognition performance can be achieved with a lower number of images in a set. These are the key related works for this research. And at last, authors would like to thank the NSERC and MITAX for the partial support of this research in the form of DG and SPG grant. Thank you for listening. We will now be accepting live questions for 10 minutes.